Hello dear students. So, in today's class we will continue our discussions on the formation of cloud droplet or on the formation of rain droplet from the cloud droplet. Right. So far in the discussions of atmospheric thermodynamics or in cloud physics, we have seen what is the process of water vapor condensing to form tiny droplets of water, a collection of which we call as clouds. Right. So, we have seen that what are the two effects which play very important role in the formation of clouds or the droplets. The two effects were called as the solute effect and the curvature effects. These effects are important in the sense that they will try to intercompete in the formation of the droplets, right. So, we have seen that one will try to increase the saturation vapor pressure and another will try to decrease the saturation vapor pressure. We have also seen how these two effects can be combined and which term is important and under which circumstances is this term important. We have seen all this, right. So, in today's class we will try to derive a mathematical expression for the radial growth of a droplet. So, now we see that once the water vapor, let us say if you have water vapor, if you have small tiny particles which you call as the cloud condensation nuclei which are available. So, these cloud condensation nuclei will not allow the mixing ratio or the amount of moisture to increase beyond the saturation. So, the moment when the saturation is reached or when it is equal to 99% at least, they will immediately behave as the surfaces over which condensation can happen, and as a result if the condensation happens you will get the droplets, right. So, the ideal situation where you will require several hundreds of relative humidity is never actually needed, right. So, having said that, so we have seen what are the curvature and the solute effects. These are very important in understanding the cloud formation. So, curvature effect and the solute effect, right. We have also obtained an expression for that, right. So, this is the combined expression where what will be the saturation vapor pressure with respect to a curved surface in the presence of a solute, right. So, we know what are these A and B terms, right. So, in today's class what we will see is we will see the diffusional growth of a droplet. So, what are we trying to do here? So, we have seen that once the tiny droplet forms in the sizes of typical micrometers. So, what this droplet will do is this droplet has to grow to larger sizes. How does it grow? It grows by two different mechanisms. Let us say one is by diffusion, where water molecules from the surroundings will diffuse into this and they will contribute in the increase of the size of this droplet, right. And another mechanism is, let us say, is by collision and coalescence. What it does is by collision, let us say. What it does is, if the droplet has acquired some size or if the droplet is moving, it will come in contact or it will collide with several other molecules or tiny droplets. What they will fix themselves, they will stick to the droplet and they will contribute in the growth of this particular droplet, right. So, today what we will do is we will try to see how the radius of a droplet will change with respect to time. So, we are going to obtain an expression for the rate of change of the radius of a droplet with respect to time. Eventually, what we are trying to look at is how the droplet will grow in size with size with respect to time, how it will change, right. So, let us say for this discussion what we will do is we will start from the standard Clausius-Clapeyron equation, from which we will try to understand the radial growth of a droplet. So, the topic is the radial growth of a droplet by diffusion. You may also see it as diffusional growth of a droplet, right. So, this is the topic, right. Now, let us assume that EVS is the saturation vapor pressure of water vapor. EVS is the saturation vapor pressure of water vapor. And rho is the density, right. So, we can write that E dES by dt according to the Clausius-Clapeyron equation is latent heat divided by temperature into alpha Vs minus alpha L, right. So, where alpha L is the specific density of bulk water or liquid. So, alpha is the specific density. So, we know that the density is mass per unit volume and 1 by rho is alpha, right. So, alpha L is the specific density of liquid and alpha Vs is similarly the specific density of vapor at saturation. This is more important, right. Now, let us say we take this equation, this is going to be the starting point, we take this equation, we will try to rearrange this and we will try to incorporate many other terms which are relevant for the droplet, for the vapor or for the radial growth, how the mass changes. So, you have to understand that if the droplet is growing in size, its mass is also increasing. So, this radial growth has to at some point also involve the mass, right. So, we can rewrite the expression for our convenience, so which is dES by dt is L by T into 1 by rho Vs, the density of water vapor at saturation minus. So, what I have done is I have used alpha, the specific density, as 1 by rho. So, which is, so I am going to just use the simple rearrangement of this equation. So, which is basically algebraic rho L minus rho Vs divided by rho Vs times rho L, or L rho Vs divided by T into 1 minus rho Vs by rho L. So, what is rho Vs? Rho Vs is the density of saturated vapor. So, and rho L is the density of the liquid. So, for obvious reasons we can say that the density of water vapor at saturation will be very, very small in comparison to the density of the bulk liquid, right. So, we can use this into this equation, right, and we will say that, so dES by dt is simply equal to rho L times rho Vs by T. Okay. Let us call this equation, what have we done so far? We have just used the Clausius-Clapeyron equation for between the density of water and the density of vapor at saturation. So, we have gotten rid of the density of liquid because the term is appearing in the denominator, which is very large in comparison to the term that appears in the numerator. So, we can neglect this entire rho Vs by rho L, and as a result we can write the change of the saturation vapor pressure with respect to the temperature is equal to the latent heat times the density of water vapor at saturation divided by the temperature. Right. Now, we have to understand that the water vapor satisfies the ideal gas equation. So, how does it look like? ES. ES is the pressure. Because it is a partial pressure, you call it as the you call it as the vapor pressure. ES is the pressure that is exerted by the vapor on the surface, on the bulk water, is rho Vs at saturation. Density of vapor at saturation times RV. You use the gas constant for the specific vapor, not the universal gas constant. So, this is the specific gas constant which is for the water vapor. So, RV is the specific gas constant for vapor, right. So, we can write that we take a derivative of this equation with respect to the temperature. So, this is ES is always the vapor pressure. To indicate that, we use E instead of P. Okay. So, this is equal to d EVS by dt times RVT plus rho Vs into RV. So, this is just a derivative, the derivative of the vapor pressure, saturation vapor pressure with respect to temperature is. So, this is now a function of temperature. So, this term appears here, RVT appears as it is. Then the rate of change of temperature with respect to the temperature is 1. So, the remaining part comes in the as the second term in the equation. So, let us call this equation. So, we have this equation as, let us say we have this equation as A, and now let us call this equation as B. Okay. So, if this is B, so now let us equate equation A and B, equate A and B. So, for why are we equating? So, for the rate of change of vapor pressure with respect to the temperature, what we will get is, so L times rho Vs by T is equals to d rho Vs by dt times RVT plus rho Vs times RV. Okay. Now, let us divide this equation with rho Vs RVT, okay, which we will get as L rho Vs divided by rho Vs RV T square is equals to d rho Vs by dt into RVT divided by rho Vs into RVT plus rho Vs into RV divided by rho Vs RVT. Okay, so we can cancel this. So we can rearrange this expression for simplicity as L by RV T square is equals to d rho Vs by dt into 1 by rho Vs plus 1 by T, or 1 by rho Vs d rho Vs by dt is equals to L by RVT square minus 1 by T, right, or d rho Vs by dt is L by RV L by RV times dt over T square minus dt by T. Okay, let us say we keep this equation, we are going to use this. So, this is, so let us see what we have got. We have got the rate of change of vapor density at saturation with respect to the temperature. The change of vapor density at saturation with respect to the temperature is equal to L is the latent heat that is released when condensation happens, RV is the specific gas constant, dt is the change of temperature, T is the temperature itself minus dt by T. So, where have we started? We have started at this point. So, we have started with this basic equation which gives you how the saturation vapor pressure will change as a function of change in the pressure or change in the density with this, right. So, we have used this equation and we have rearranged this equation in just so that we have vapor pressure on the left hand side and we have the density on the right hand side, right. So, in addition to, so this is equation A, then we said that the water vapor obeys the ideal gas law. So, we taken the ideal gas law in terms of the specific gas constant, we have taken a derivative, we have equated these two terms and we have equated these two terms to obtain the rate of change of saturation vapor density with respect to the temperature. Right. Now, let us say we integrate this equation. Now, we integrate this equation from a temperature. So, this is with respect to temperature, right. So, this is the denominator or the variable with respect to which the change is recorded is the temperature. So, obviously, the integration has to be carried over temperature from, let us say we call a temperature TE to TR. So, what is TE? Where TE is the ambient temperature, TR is the temperature at the surface of the droplet. So, we have a picture in which you have an ambience. Let us consider a single droplet for the case of simplicity. So, this is the temperature of the ambience is TE, the temperature at the surface of the droplet is TR. So, we are integrating from this to that, right. Now, let us say if you do that, so that will be integral d rho Vs by rho Vs is equals to L by RV integral dt over T square minus integral dt over T. So, the integration limit is, so it has to be converted from temperature to density TE to TR, or we will say ln rho Vs from TE to TR is equals to L by RV minus 1 by T between TE to TR minus ln T from TE to TR, right. Now, let us call the density at the temperature or the droplet as rho Rs saturation at the radius and density at TE as rho Es. We are going to use this into this equation. Then we will rewrite it as ln of rho Rs. Now, it is obviously at saturation, but where is it? The density is now being calculated at the radius of the droplet, where the temperature is identified to be TR. That is I am conveniently calling as rho Rs by rho ES. The density of the ambience at saturation, right, is equals to L by RV times 1 by TE minus 1 by TR minus ln TR by TE. Okay. Let us say we consider this as a intermediate result which we have to use, right. So, what have we done? Now, we have having got an expression for the rate of change of density of vapor at saturation in terms of changes of temperature and the latent heat and the specific gas constant. We are in a position that we have integrated that to obtain parameters with respect to two points, let us say one in the ambience and one on the droplet itself. Now, when will diffusion happen? Diffusion will happen when there is a density gradient, of course, and when the water molecules which are present in the vapor phase stick to the droplet and the droplet will grow, right. So, let us say we will take this equation forward, right. Now, we have two ln terms appearing here, right. So, we will use an approximation, let us say for what is the nature of approximation? For very small values of z, z is just a variable, okay. We will write ln of 1 plus z as equivalent to z, right. Now, in this case, so let us say we have ln of y by x. So, we can write it as ln of x plus y minus x divided by x, or ln of 1 plus y minus x by x. According to this, let us say, let us call it as a again, is due to a is equivalent to y minus x by x. Now, for this to happen, we need for this approximation to work, we need y minus x by x very small, right. Y minus x divided by x becomes very small when x is very large and or y minus x is itself is very small. These two are the cases, right. Now, so why are we discussing this in the first place? We are discussing this because we want to address how we can simplify this term ln TE by TR. So, for this approximation to work out, we will simply have to demand that TR by TE is very small. Okay. So, let us apply this and apply this. Let us say we call this as B and let us say we call this as C. Now, applying B and C in ln of rho RS by rho ES is equals to L by RV to 1 by TE minus 1 by TR minus ln TR by T. Okay. When we apply this, we will get rho RS minus rho ES divided by rho ES is equals to L by RV to 1 by TE minus 1 by TR minus TR minus TE divided by TE. Simplifying this algebraically, rho RS minus rho ES divided by rho ES is equals to L by RV into Tr minus Te divided by Te, Tr minus Te divided by Te. Okay. Or rho Rs minus rho Es divided by rho Es is equals to Tr minus Te divided by Te. Pulling this out, we will write L by Rv Tr minus 1. So, this is how this vapor pressure at saturation changes. So, what this expression tells you is how the vapor pressure at the radius or the difference of vapor pressure between the droplet surface and the ambience, let us say this is the ambience and this is the droplet surface, how the difference of vapor pressure is with respect to the ambience, how large is it or how small is it. How it varies is given by the variation of temperature at the radius and the ambience multiplied by a term which is the latent heat divided by the specific gas constant of water vapor Tr minus 1. Right. So, we will stop here. So, we will continue this and we will try to see how we can get from here to an expression for the rate of change of droplet radius with respect to the temperature. Right. So, we will stop here. So, we will continue this discussion, this mathematical discussion in the next class. So, our objective is still to find an expression for the radial growth of a droplet, of a cloud droplet. Okay.